Hello, welcome to my keynote speech. My name is Tim Webster. I'm with the Applied Geomatics Research Group. Pleasure to be here, and I'm going to give you a little talk on what I've observed with LiDAR the last 20 years. So this is not meant to be exhaustive, but just going through some of my experience. I'm with the Applied Geomatics Research Group at NSCC. So first, LiDAR is an acronym for Light Detection and Ranging. I'd like to lobby that we spell it lowercase LIDAR rather than the caps. LiDAR is now ubiquitous, similar to radar and sonar. We no longer put caps on those names. They are mainstream. So that's my pitch. The principles behind laser ranging and LiDAR is we emit a laser pulse, and we then watch for the reflected signal to come back. We measure that time from transmission to reflection, and we take that two-way travel time, multiply it by the speed of light, divide by 2, and that gives us our range. Now, you'll notice in the lower right here, I have two graphs showing two different returning waveforms and a line marking what the time signal would say that waveform returned at. So the shape and the amplitude of that intensity of the waveform can actually affect the timing. Now, it wasn't until inertial navigation systems with survey-grade GPS and inertial measurement units came along that we finally had an integrated airborne LiDAR system, often coupled with a camera. This looks like more of a push broom camera, but oftentimes these are frame-based cameras. The IMU typically measuring at 200 kilohertz, 200 hertz, 200 times a second. Now the latest are up to 500, and the GPS 1 to 2 hertz. Pitch roll usually always have a better accuracy than heading. This is because gravitational accelerations are involved with measuring the pitch and the roll, not so much on heading. Moving up to the common wavelengths, we've got the bathymetric LiDAR sensors for penetrating the water, 515 and 532. Then we move up into the near infrared. We've got sensors out there, 865, 905. By far, the most dominant wavelength is 1064 for the traditional topo LiDAR mapping. And then 550 is also a common wavelength. Now let's talk a little bit about the details of the laser system and so forth. So first we have the beam divergence. So this is how much spread the beam has. Typical topo LiDARs have a very narrow beam divergence. So for example, if a beam divergence of 3 milliradians at 1,000 meters, you've got a 30 centimeter diameter footprint on the ground. Next, looking at swaths and scan angles. This is showing on the left-hand side the old sawtooth pattern of some of the earlier systems that used to oscillate a mirror back and forth. A lot of these have been replaced by rotating mirrors, and many with elliptical or circular scan patterns. Now, with respect to the pulse, the repetition pulse frequency, RPF, back in 2000, some of the first LiDAR surveys that I was involved with, 5 kilohertz, 5,000 shots per second. In 2021, systems were coming out with 2 million shots per second. And I guess the other point I want to make there is that the separation of objects, how close they can be, is really a function of the pulse width. So how long the laser pulses when it sends out that first initial pulse. Lastly are the returns. The original LiDARs were either first or last. Eventually they became first and last. And now, of course, we have a whole variety of one pulse gives us multiple returns in terms of points that are processed. The big players today, Leica's got the terrain mapper and the city mapper, both at 2 megahertz. Optec has the Galaxy sensor, 2 megahertz as well, a couple of different beam divergence there. And Regal has the 2 LiDARs, 2 lasers, each at 2 megahertz, giving you a total of 4 megahertz. So really come along. Now, this is a sort of a diagram from the past, but it still holds true today. Many systems take the waveform data and process it during time of flight into the discrete points. LAS is still the standard format for delivery of LiDAR data, a binary format. We're now up to 1.4. When the data is first processed, the data is processed into strips or flight lines. We then have to take it into a software package and tile it up into smaller chunks in order to be able to process the data. TerraScan is the standard by TerraSolid today. And the last file's got all kinds of other information, echo code, intensity, the GPS time, the scan angle, and so forth, all very important. And also remember that the inherent elevation of the LiDAR is ellipsoidal height, and then we'll sometimes change that to orthometric height. On the left-hand side here is a showing the trajectory of a series of LiDAR flights. That's the first step, is to process the trajectory of the aircraft. Then we link the scans to it. Here we can see a 50% overlap in the scan pattern. And then lastly, we see a cross-section of a LiDAR point cloud that then goes through classification, and we're showing here the ground points. So the classification is, of course, very key to actually how we use these data in GIS. Here is the Annapolis Valley in Nova Scotia, and this is some LiDAR collected back in 2000. So this shows a Landsat image, 30-meter pixels, some road areas, and so on. You can see the roads and the cleared areas are painted with the LiDAR, extremely dense point density. Sparser in the canopy area. This was flown with leaf-off conditions. And now we have the digital surface model, which is an elevation model, but we can see the roads and the cleared areas. We go from blues being at sea level up to the top of the mountain, in the oranges and reds back into the Annapolis Valley. We remove the trees, and here's the real power of LiDAR. We can see the drainage patterns very well. We can see these ridges in the bedrock. These are different volcanic layers. And this is really the power of topographic LiDAR to penetrate the vegetation canopy. Prior to this survey, this was the best available data for the province. 20-meter, derived from photogrammetry, stereo pairs, full of artifacts. Luckily, though, the province of Nova Scotia is now covered totally with LiDAR. This is that same area I showed the trajectory for. This is Musquash in New Brunswick, a salt marsh area. This is the LiDAR DSM, the digital surface model. Here we have the LiDAR intensity. So this is the 1064 amplitude of the reflected signal, more or less shows up as a black and white air photo from that 1064 for all of the LiDAR points. So this would be an intensity of the DSM, if you will. We can then hybrid those two, and we've done some work on how we can use these different derived layers to doing object classification. We published that back in, when did we publish that? 2006, back in Canadian Journal of Remote Sensing. Okay, lots of applications of LiDAR. They're growing all the time. Forest inventory, corridor mapping, power line, railroads, etc. In the geological world, lots of mapping going on, not only to identify potential geological structures, but also logistics for road and volume estimates. City mapping with digital twins is becoming very popular. Obviously, deriving watersheds and streams, like I just showed on the North Mountain, extremely valuable. Floodplain mapping has been the bread and butter of topo LiDAR for a long time. Archaeology is coming into play. Now, I do a lot of work with bathymetric LiDAR, and this technology has really evolved. We go from some of the early systems, like this huge Fugro LAD system, and the Shoals was a very large system as well, requiring large aircraft. These older deep water systems would typically go 2 to 3 Secchi depths. And the Secchi depth is where we lower this disc down in the water and we lose sight of it. Now there are some shallow water systems coming out that have been out since the mid-2010s that can go 1.5 Secchi depths, much cheaper, and everything is getting smaller. So the current systems on the market is the Leica Hawkeye, that's a deep water system. The Chiroptera 5 is a shallow water. The Regal 840G is a shallow water. Fugro has the Seasmill Supernova, that's a deep water system. And the Fugro Rams is a proprietary system. We're starting to see Bathy LiDAR come onto drones, but I would say it's still not a really proven technology in that regard yet. We own the Chiroptera system. It's a 4X obtained in 2014. 500,000 shots on the near IR laser, 35,000 on the green laser. It's also equipped with an RCD 30 60 megapixel camera. It scans in an elliptical pattern, 14 degrees forward and back, 20 degrees side to side. The near IR is used for topo and mapping the water surface. The green laser will go through the water column. However, it slows down, so we need to know where the water surface is to adjust for the refraction angle and the change in the speed of light when we process the waveform, which shows here for the green laser, strong reflection on the sea surface and then a reflection off the seabed in order to calculate that point in the right position. This just shows the real-time waveform to show that we're getting good data and the setup inside the aircraft. Here would be a typical profile from a shallow water system. So we got to about 11 meters. If we added the deep water channel, this can extend us down to, in this case, 20 meters. This is an interesting graphic a colleague of mine made. This is taking a given scene and plotting the intensity versus elevation above the ground or depth below the water. So here is the vegetation on land from the passive camera, very little penetration in the water as we would expect. The red band, the green band, and the blue band of the camera are quite similar, showing essentially how the seabed drops off with intensity as we move deeper. This would be depth on the y-axis, intensity on the x-axis. The LiDAR is quite interesting. Here we have the near-infrared on the surface, and the bathymetric returns from the 515 nanometer laser. This would represent the seabed, this curve, and this cloud represents vegetation. So that's what I'm going to talk about now, is how bathymetric LiDAR is used for benthic habitat mapping, so seabed classification. Here are the classes that ASPRS has proposed for bathymetric LiDAR, 40 being for bathymetry, 43 being submerged objects. This is up near New Brunswick, Taos and Tack. Here is the intensity map, so light areas being sand, darker areas being seaweed, in which case this would be eelgrass, seagrass. We then go out and do some ground truthing, collect where there is seagrass, and we've made this map showing essentially the height of the seagrass, blues being the highest, yellows being no seagrass, and greens being intermediate. We compare that to an echo sounder technique from a biosonics instrument, and we can see good correspondence between what the echo sounder is seeing for seagrass compared to what the LiDAR map produced. We then can take and make a binary map of presence absence. We compare that to our ground truth point sampling. We get about an 86% agreement. If we compare it to the biosonics, we're actually up to about a 92% agreement. We use the biosonics instrument really for ground truthing our LiDAR data set. It's good, but it only does profiles. And of course, the LiDAR shows us the entire bay. These are pollution sources. So here's another application of bathy LiDAR. And the seamless DEM is to essentially develop these nearshore hydrodynamic models. In this case, we're looking at the fate of pollution. And for many of these bays, the pollution never really leaves the bay. It does not flush with the tide as many people would expect. This was a project we did on shellfish aquaculture. Another area that's becoming very common and big in LiDAR, bathymetric LiDAR, is looking at surveying rivers for improved flood risk mapping. The river channel is the biggest challenge to map today. And of course, topographic LiDAR does not penetrate the water column. Here's a series of GPS points. The blue is essentially the bathymetric depth from the LiDAR, and the orthophoto is behind that. So here we have our GPS points, and you can see very good agreement. If we look at the DEM, and there's yours truly out, almost to 2 meters depth, collecting some GPS, we could see that we've got a mean difference of 9 centimeters, a standard deviation of 8 centimeters when we map that channel on the DEM. So pretty good. Now, all of this is to eventually produce flood risk maps for the river. Here is the original channel. Our cross section was about here. We just looked at. And here, for example, is the flood depth of the 300-year return period. And we could produce velocity and other hydrodynamics from that. So bathymetric LiDAR is really improving that area. Next, let's move on to terrestrial LiDAR. There are a variety of survey instruments out there for laser scanning. We've got experience with the Optec, first the Ilris and then the Polaris. Lots of people doing some interesting work in forestry with terrestrial LiDAR and work indoors, etc. This is some work we did along these steep bank features that the topographic airborne topo LiDAR didn't do a great job in cliffs and certainly overhangs and so on. The original Ilris we would have to deploy targets. You still do with these types of terrestrial tripod-based scanners, and then georeference those, and then essentially you've got your scan. Quite labor intensive, and this has been superseded eventually by mobile mapping. But first, let me show you a series of scans, and the red and the orange were done, yellow, I should say, prior to a storm, the green after a storm. So we can see the amount of volume along this section of coast that that had been mapped out and how much material had been lost after a significant storm. This has been superseded by mobile mapping, and here we're integrating the laser scanner with the IMU and GPS inertial navigation system. So now this allows us to, in this case, motor along the shore and collect direct georeference point clouds. The ATV, you'll notice we have 2 antennas here to help with the heading. Here's an example of driving down in a rural area with that Dynascan mobile mapping system and mapping all of the street furniture and the power lines directly with that unit. So there are lots of improvements to that technology. Okay, I want to wrap up the talk with a quick example of a big event that happened last September here in Nova Scotia. Hurricane Fiona made landfall. We had 14 hours of over 100-kilometer-an-hour sustained winds along the Northumberland Strait and severe damage. Now, we've developed a web-based platform that gets the prediction from Environment Canada 10 days in advance of a storm surge, and it marries it with the tide. For example, here we're looking at an area on the north coast of Nova Scotia, looking at the predicted tide gauge of Pictou. That would be in orange on this graph. The surge, which was predicted to be 2 meters of Fiona coming in ahead of time, is in blue. And then we add those two to give us the total still water level up where the surge plus the tide. As we move around on the chart, the flood map automatically updates, which is based on a LiDAR DEM, or we can raise this slider bar. So this water level does not account for wave runup. So it was 2.1 meters above CGDV 2013. The predicted for Port Hood was 1.8, a little less in Malagash. And here we see the wind at Caribou as Fiona made landfall. The wind shifted from the south into coming from the north up to on the order of 100 kilometers an hour. These yellow values are where we've gone out and measured the actual debris line or the rack line of where the water pushed to the farthest. And this incorporates wave runup. And from looking at the predictions versus the observations, we think we had about a 0.8 to 1.2 wave runup. And I'm going to show you some more details of that in a moment. This was an area we had done some of our study. This is where I showed you the laser scanning a moment ago. Here we could say, okay, let's bring the sea level up to 2.1 meters and then add some value for wave runup. So here's an ortho photo with the water level raised up and showing the potential inundation at 2.9 meter water level. So this would be assuming a 2.1 meter surge tide combination and a 0.8 meter wave run up, would show, potential flooding into this building and then flooding up through the yard and so forth. We then came back after Fiona and we had severe erosion behind this armor stone, severe erosion of this bank and the debris line. These are boulders as well as debris of various grass, boards, everything else that could be in the water. And you see we had very good agreement. So we've gone out and mapped this rack line and correlated with either GPS or LiDAR to come up with these total water levels that I showed you previously in the yellow font along the coast of Nova Scotia. So here we can basically tell that we had about a 0.8 meter wave run-up value, and the prediction of the system came out quite well. We were quite pleased with it. Here's an example of a perspective view of the drone ortho draped over the DEM, the DSM, I guess, in this case, before the storm, and then after, showing the same shoreline. So a good idea of how much material was eroded, and looking at it in perspective view gives you a nice view that way. Okay, last slide before my conclusions. LiDAR has certainly gone mainstream when Apple starts incorporating it into their iPhone and iPads. Still early days, but lots of different, LiDAR is becoming ubiquitous for sure. So to conclude, LiDAR has been around since the 60s, took finally navigation systems to catch up, and in the 90s, we had airborne LiDAR. First from 5,000 hertz to now 2 million hertz and multiple returns per pulse. The last file is still the standard. And of course, we can integrate imagery with the last data sets. Bathymetric LiDAR, lots of work there for ecosystems and rivers, starting to really grow. Terrestrial LiDAR, still growing, the cities, the BIM. What I didn't have a chance to talk about today, though, was SLAM, Simultaneous Location and Mapping, which is really how LiDAR scan data can be used in a GPS-denied environment, indoors, in a cave, etc., to really be able to align your scans. So lots of different wavelengths, beam divergence to fully understand what the LiDAR data is showing you. And I think it's still superior from structure for motion with the other data sets. So in that regard, I want to thank you very much, and I will stop my recording. Thank you again.
Well, thank you very much, Tim. That was informative as always. I remember your lectures very well from back in the day. Can you tell us about your current research goals at the AGRG? Are there any particular projects you could speak to right now that are interesting?
Sure, John. Thank you. You mentioned about trying to map kelp. So we have an insert project where we're partnered up with folks from Holland College out of PEI and College of the North Atlantic, where we've flown Bathy LiDAR and are trying to map kelp. We're also doing other projects looking at shoreline erosion and so forth. I do see a few questions though popping in here.
Yeah.
And I guess I want to thank Fiona for agreeing with me that we should switch to lowercase LiDAR. I see she also had another follow-up question here. How was LiDAR used to track pollution, and what is it detecting? So to be clear here, the LiDAR provided the foundational information, the seamless elevation model at a high resolution. We then developed the hydrodynamic model to move the tide in and out, and then we released particles of a certain buoyancy and have a certain decay rate representing bacteria. That's what those red objects were. So they were not detected by the LiDAR, but the LiDAR is critical to providing that foundational bathymetry and elevation data to drive the model. So I hope I clarified that. The LiDAR really wasn't picking up any bacteria, but rather was the basis. You mentioned Bathy LiDAR is unproven at the mobile scale. Is there any specific obstacles where we can be mainstream? Obstacles before we can see mainstream adoption of the LiDAR. So based on the green LiDAR. Yeah. So what I've seen so far for drone-based LiDAR, first, it's only a green laser. There's no near IR laser in the one product that I've looked at. So therefore, the approach that the drone LiDAR is taking, however, is extremely high density of point collection. And without the near IR laser, there's always a bit of a question about the accuracy of the green points. Now, undoubtedly that will come along, and certainly that point density will have its application in certain projects. Now, Of course, anybody that's worked with drones, and if you go near the coast, you'll know there's always wind, and drones are fairly intensive in terms of battery use. And of course, LiDAR being an active sensor, these will be, I think, some of the barriers that drone-based bathymetric LiDAR will have to overtake. I see one popped here. What is the depth that bathymetric LiDAR can penetrate? Well, that's a tough question. It really depends on the water clarity. Two things: water clarity and reflectance of the seabed. So when we're planning a LiDAR, bathymetric LiDAR survey, we have to be a little more rigorous than with a topo survey. So for example, a storm could come through, have rain and wind. The next day, if the weather's fine, you're probably good to fly topo LiDAR. Topo bathymetric LiDAR, however, if you have any kind of wind along the shore or runoff into rivers, and those rivers become turbid or murky, then that will just scatter the light and you will not get good penetration. So you need to wait a few more days for that water to settle. Secondly, any kind of water that has a lot of tannins in them, that are very dark colored waters, they're typically not suitable either. So on the Atlantic coast, the shallow water bathymetric LiDAR system, we've gotten out to 15 meters. In certain areas, you know, the Caribbean and other clear waters like that with sandy bottoms, they're out farther with depths. Is there a future for underwater LiDAR surveys to get depths below 20 meters? So I think the question here is asking me, putting the LiDAR under the water as opposed to above the water. You know, I really don't know much about that question, or that answer, I should say. I just want to know, as per accuracy for BIM purpose, which one is best, SLAM or terrestrial LiDAR? That's a great question, Cassie. SLAM is really a technology for seaming together your scans in a relative orientation. So they will get collected and processed and will be aligned to each other relative. When you start to ask about accuracy, I automatically think about absolute accuracy in terms of a coordinate system and so forth. And there, deployment of targets or some kind of control is required. So, you know, it's a little bit of a toss-up between the terrestrial LiDAR and the SLAM. The SLAM is definitely more efficient for moving through and collecting the data, and does a great job for relative orientation. And with control, you then can bring that into absolute accuracy. Terrestrial LiDAR, you're using control right from the get-go typically.
Great. There's a question I've got related to skill sets, Tim. When I was at the AGRG, we came out through the GIS program or the remote sensing program at COGS. I'd be curious, what's your take now, 20 years on what are the skill sets do you think someone should really have to be a great professional working with LiDAR, processing, data collection? What does that skill set look like?
Sure. Well, not many institutions have access to the actual hardware. So if you can at all ever get access to see the hardware in operation, or understand, go to a trade show and talk to the LiDAR providers to understand what how the hardware itself works, that's important. But of course, the broad range and the more populous jobs will be processing the data. So certainly to have a knowledge of those things that I talked about, you know, beam divergence, scan angle, pulse width, etc., are important when you really want to get into the fine details. Probably not everybody needs to know that, but if you really want to get into the details and understand the interaction of the laser with the features on the ground, those are all important things. With respect to the most common practices out there, one, to learn about processing the point cloud, tiling it, classifying it, extracting derived products from it, LiDAR intensity, surface models, etc. Then after that, deciding, is it best to be in a raster format, like a digital surface model or elevation model, DEM or DTM, or in the point cloud. And then, of course, you're then into your GIS environment where virtually the sky's the limit, no pun intended, for the applications of that high resolution data, whether it's in the BIM environment, whether it's in the natural resource environment, whether it's in the public safety realm. Once we get the data to that stage, then you're really looking at GIS spatial analysis being a core component for being a LiDAR professional. So knowledge of the point cloud, how to process the point cloud, and then what to do with it once it's in either the raster format or still at the classified point cloud level.
Great. Thank you so much, Tim. Thanks for your keynote. Thank you, everybody, for your questions. We've gone into our break a little bit. So after the break, we're going to come back. We've got a great talk with Sven from NV5 Geospatial. Looking forward to that. Tim, you're going to be doing the moderating and Q&A. I'll be back at the end of the day to say hello and goodbye to everybody one last time.
I see there's one last question here, John. Do you mind if I answer?
Oh, yeah, go for it.
What from Jay? What could be considerations for conducting bathymetric river LiDAR in rivers? So first off, number one, water clarity. So if you've got a fairly clean water river, you want to try to hit it with bathy LiDAR. So first off, then it could be successful for bathymetric LiDAR. Secondly, ideally, depending on the depth of the water, you want to probably hit it at base flow level. So at the lowest possible water level, increases your probability of getting deeper depths or getting to the bottom in areas if you have some pools and so forth. Lastly would be, considerations around weather and making sure that you're not trying to fly right after a rain event where maybe you have things coming from the watershed into the river to affect the water clarity. I didn't mention the river bed itself, but of course, a dark, mucky, black bottom of a riverbed would not be as conducive as, say, a nice gravel bottom or sandy bottom riverbed. So the bottom is the other thing. So water clarity, low water, clear or reflective riverbed bottom, and avoid rain events and things like that. Those are the main considerations when conducting a river survey.